Red Vision is a new line of SparkFun products intended to make computer vision on microcontrollers easy and practical. As part of this effort, we created a MicroPython port of OpenCV, an extremely popular open source computer vision library. Watch our other video to learn more about it, but in short, OpenCV has loads of algorithms that you can chain together to create vision pipelines to extract useful data out of images. We launched Red Vision with a kit for the XRP robot that includes a touch display and camera, and now we're bringing those same components to the RedBoard form factor with the new Red Vision kit for RedBoard. I'll give some brief setup instructions and then we'll do some fun demos. First off, you will need to choose a development board to use, and I'll be using the IoT RedBoard RP2350. Note that as of filming, this is the only RedBoard that fully supports the Red Vision kit. Then we deflash the Red Vision firmware onto the development board. Note that this will delete all files on the board, so back them up first. The flashing process is different for every board, but for this one, just plug a USB cable into your computer, then hold the boot button while plugging the cable into your board. Then it will run the bootloader, which causes the board to connect as a USB mass storage device called RP2350, where we can drag and drop the firmware file to program it. To get the Red Vision firmware, go to github.com, then within the SparkFun fork of MicroPython, go to the Releases tab, then under the latest release, show all available assets, and the Red Vision firmware files are at the bottom. I'll download the one for the IoT RedBoard RP2350, then drag and drop the firmware file into the RP2350 folder. This firmware is much larger than standard MicroPython, so be patient, it can take a minute to finish. Once done, the board will disconnect, then reconnect as a serial device. Open your favorite MicroPython editor, I will use PyCharm. Once connected to the board, you'll see a folder called Red Vision Examples, which includes various examples you can run to confirm the hardware is working, and it highlights various image processing techniques. Before we can run the examples, we'll need to attach the Red Vision kit, so I'll unplug my board for now. Hardware assembly is super simple. Just insert the display into the headers of the development board, then insert the camera into the socket. And that's it. Just be careful to insert the camera into the socket correctly. There are a number of DVP or digital video port cameras on the market with this same form factor. Most have 2x9 headers, but some have 2x10 headers with the last two pins duplicated. So the socket is 2x10 for compatibility with both. You just need to keep cameras with the 2x9 headers left justified. The pinout is also indicated with the silk screen next to the socket. I've programmed my board to run one of the examples included with the Red Vision firmware, and I'll give power to the board with a battery pack to prove that all processing is happening on the device. When I power it up, the Red Vision splash screen is displayed briefly, and now we're seeing a live view from the camera. You'll notice some annotations on the image because this example creates an OpenCV pipeline to try and detect an object. It's a very simple pipeline, so there are some false positives, but if I hold this paper in front, you can see it's detecting the SparkFun Flame logo. Again, all processing is happening on the RP2350. This example runs at roughly 2 to 3 FPS with a 320 by 240 resolution, which is obviously not super fast compared to a desktop computer, but it's quite respectable for a little microcontroller. Another feature of the kit is that the display includes a capacitive touchscreen, so you can use it for inputs. I will connect my board to my computer so I can run the provided example for that. This example lets you draw on the screen, and I'll draw a little face, but the touchscreen can also be used for whatever you want. Maybe select a region of an image that you want to process, or perhaps create a user interface of some kind. You can get very creative. So that's what's included with the base Red Vision kit for RedBoard, but you can also swap out components if you want, assuming there's software support for it. Like I said earlier, there are other DVP camera boards on the market with the same form factor, such as this board with the popular OV5640. The base Red Vision kit uses the HM01B0 because it requires dramatically fewer GPIO pins than other cameras, but the downside is that it outputs a raw Bayer image that has to be demosaiced. Color space conversions like that take time, usually tens of milliseconds or so it limits the maximum frame rate you can achieve. The HM01B0 also has no color grading, so the image is rather green with some vignetting that makes the corners dark. In contrast, the OV5640 requires a lot more GPIO pins, but the upside is that it has a more advanced image signal processing built in. This means the image colors are more true to life, and it can output in multiple different color spaces, so demosaicing is not required. This also enables a fun party trick. The camera and display can be configured to share the same buffer and memory, so as long as the camera and display are using the exact same resolution and color space, then almost zero processing needs to happen in order to display the images from the camera, and you can achieve the maximum frame rate. There's a provided example that does this, which I will run now. And once it starts, you can see we're getting a smooth 30 FPS video running entirely in MicroPython. Admittedly, the hardware peripherals are doing all the heavy lifting, but I still find it amazing that this is even possible on tiny microcontrollers like this. The camera driver is running in a continuous capture mode, so it's constantly overwriting the display buffer with new images. If you want to display other images, you have to stop the camera driver, display the image, then restart the camera driver to restart the live video stream. Also keep in mind that OpenCV algorithms in MicroPython take tens or hundreds of milliseconds to compute at just 320 by 240 resolution, so you're never going to get this kind of frame rate when running an actual vision pipeline, but it's still a useful technique if you just need the unaltered camera view. Now, we've been hunched over this small display, but wouldn't it be nice if we had something bigger?
Hey, look at this!
Yes, really. The RP2350 Red board has the HSTX connector, which can be used for high-speed data output. Combined with a 22-pin FPC cable and the HSTX to DVI breakout board, you can connect to any display with an HDMI port. I'll work on getting this all hooked up. Note that I might say HDMI and DVI interchangeably. The reality is that the RP2350 sends a DVI signal through the HDMI connector, and the HDMI standard is backwards compatible with DVI signals. Also, if you only want to output to a monitor and don't need the touch display, you can instead get the non-display version of the Shield. It has the same socket for a camera, but if you don't need that either, you can also just get the Red board by itself. The demo I cooked up does use a camera and both displays, so I'll put this boards back on, and now I'll run that demo. Now I'll run this code, and you'll notice that the Red Vision touch display immediately shows the splash screen, and the monitor does show it as well. It just takes a couple seconds sometimes with monitors like these after the display signal is actually sent. But you can see we're getting an image now, and my script that I'm running here is waiting for me to press the spacebar on my computer, and then it will take an image from the camera and display it on the screen. So I'll get framed up. And there you can see we got an image of me. And you'll notice that the touch display stays on the splash screen. That's because both displays can be run completely independently from each other, sort of like Windows and standard OpenCV. I'll read a few more images, and you'll notice that the display goes every single time I read a new image. This is a result of the display driver's image buffer being stored in external PSRAM, which is much slower to access than internal SRAM. It's fast enough for the display by itself, but the camera driver also uses the external PSRAM when reading images, so the QSPI bus that connects to the external PSRAM chip becomes a bottleneck. DVI requires very precise signal timing, so if the display driver is unable to read the pixel data from PSRAM in time, it will just send repeated rows of pixels, resulting in that. You'll also sometimes notice little artifacts at the bottom of the image, which are again a result of the image buffer being stored in external PSRAM. The pixel data gets written to PSRAM using the RP2350's XIP interface, which can end up storing some pixels in its cache without actually writing them to PSRAM. The DVI driver reads pixel data directly from the PSRAM, resulting in a memory desync that causes these artifacts. A workaround for this is to manually run the MicroPython garbage collector, which I can do by pressing C on my keyboard. And you can see now those artifacts are gone. The garbage collector forces the XIP to write its cache contents to the PSRAM, fixing that desync. For this demo, I intentionally put the monitor's image buffer in PSRAM to highlight these limitations because it really pushes the limits of the system, so good code design is required to get good performance. If you're actually using a DVI or HDMI monitor, it's best to ensure the display driver's buffer is an internal SRAM to prevent these kinds of problems instead of having to work around them. The provided examples have some more info about this, but I will run the high FPS camera example using the display with that image buffer in internal SRAM to show that the monitor can actually display a stable image while using a camera. So I will stop the previous code and I will run the other example. And it'll take a couple seconds again for the monitor to pick up that signal, but then once it does, you can see we're now getting a smooth 30 FPS video with no artifacts or One other neat thing about this demo is that the camera and display drivers are using the RP2350's DMA channels to handle all of the data transfers. So there's actually zero CPU overhead while this stream is running, which is amazing. And because the CPU is completely free, I've actually modified this example to run the same flame detection pipeline from earlier. The output of that pipeline is actually being displayed on the smaller touch display, and despite having the live view on the monitor, the pipeline is still running about the same frame rate. So it really is quite a capable platform. All of these demos have been using the RP2350 Red board. However, other development boards in the same form factor can theoretically be used with the Red Vision kit, as long as it is 3.3 volts, has a microcontroller with the right peripherals and pinout to connect to the camera and displays, and has the software to do what you need. So for example, the original AT-Megabase Arduino Uno is not going to work with the Red Vision kit, so don't even try. As of filming, we only have official support and firmware for the RP2350 Red board. However, the ESP32 Red board can also be used with the Red Vision kit. We don't offer Red Vision firmware for it because it doesn't have sufficient RAM for OpenCV, but the ESP32 Arduino core does have drivers for some cameras and displays with examples to test them. On my computer, I will run the ESP32 camera web server example and modify the pins for this setup. All right, now I've got the pins changed and I finished uploading the code. The ESP32 just started and it printed out the IP address it was assigned to our Wi-Fi network. If I enter that IP address into my browser, you can see we get a web page that was sent by the ESP32. There's a lot of configuration options for the camera, but we'll scroll past all that and hit the Start Stream button. And now we're seeing a live view of the camera being sent wirelessly to my computer by the ESP32 using the new Red Vision kit. So that's the camera, and the display can also be used with the ESP32 RedBoard, though you may need to use a third-party Arduino library. Here, I've reprogrammed my board to run an example from a display library that I found, which is a simple graphics test, but it does demonstrate that both the display and camera can be used with the ESP32 RedBoard, despite the lack of Red Vision firmware. So that's a handful of demos using the new Red Vision kit for RedBoard. Now we'll jump into the specs and details. First is the Red Vision touch display for RedBoard. The primary component is a 320 by 240 resolution capacitive touchscreen display. It's based on the ST7789 display driver with an SPI interface and uses the CST816 touchscreen driver with an I2C interface. It's designed to be a shield for any RedBoard, so it's compatible with other development boards using the same form factor, as long as the development board uses the same 3.3 volt logic levels, includes a microcontroller with the right peripherals and pinout to interface with the camera and the display, and has software for your application. The socket on top is for DVP or digital video port cameras with either 2x9 or 2x10 headers using the standard DVP header pinout, which is labeled on the silk screen for reference. To further minimize GPIO requirements, an I2C GPIO expander is included on the board, the PCA9534. It connects to the control signals of the display, touchscreen, and camera. All control signals are enabled by default, so the GPIO expander is just there for users who need to access the control signals for advanced use cases. And finally, the board is 2.35 by 2.1 inches and includes a power indicator LED. Then we have the Red Vision camera board with HM01B0, which is the exact same board in the Red Vision kit for XRP, so you can check out that video for its specs. And that's the new Red Vision kit for RedBoard. We look forward to seeing what you create with it. And as always, stay safe, be kind, and happy hacking. Red Vision is extremely popular open source. You have no idea how open source it is. To show that the monitor can show a stable, and that's the new Red Vision kit for RedBoard. We look forward image while using a camera. It's the same line. As always, stay safe, be kind, and happy. I did it. I don't know how much sense that'll actually make if people are like skipping through the video or not.